Good day everyone, this is Group 7 on Week 7 lectures coverage basic controller modes, PID, and overall transfer functions practice problems. Problem number 1 goes like this. A PID pneumatic temperature controller is at steady state with an output pressure of 7 psig. At T is equal to 0, the set point temperature is increased at a rate of 0.3 degrees Celsius per minute. The controller has the following parameters. Kc is equal to 3 psig per degree Celsius, tau 1 is equal to 2 minutes, tau d is equal to 0.2 minutes, and now we are asked, what is the pressure output after 5 minutes? We are given the pressure output, which is 7 psig. The set point temperature is increased at a rate of 0.3 degrees Celsius per minute. We also have the parameter for the controller, which are the Kc, or the proportionality gain, which is 3 psig per degree Celsius. We have the tau 1, which is the reset time of 2 minutes, tau d, which is the derivative time of 0.2 minutes. And now we are asked in this problem, what is the pressure output after 5 minutes? So to solve this problem, we will be utilizing the transfer function derived from the lecture video for the PID controller, which is P of S over epsilon S equals the proportionality gain times the quantity of 1 plus 1 over tau 1s plus tau ds, and substituting the parameters of the controller, we have P of S over epsilon S equals 3 times the quantity of 1 plus 1 over 2s plus 0.2s. And since the set point temperature is increased at a rate of 0.3 degrees Celsius per minute, our epsilon t will be equal to 0.3t. Now, taking the Laplace transform, we have epsilon s equals 0.3 over s squared. Then, substituting this to the transfer function for the PID controller, we have P of S equals 3 times the quantity of 1 plus 1 over 2s plus 0.2s times the quantity of 0.3 over s squared. And for further simplification, we have P of S equals 0.9 over s squared plus 0.45 over s cubed plus 0.18 over s. Hence, the response of the controller is P of t equals 0.9t plus 0.225t squared plus 0.18 equals P of t minus ps through the deviation variable. Getting the equation of our P of t, now we have 0.225t squared plus 0.9t plus 7.18. And from the problem, we are asked the pressure output after 5 minutes, so substituting this to our equation, we calculated P of 5 equals 17.305 psig.
For number 2, a PID controller is subjected to a unit step change in error. The control parameters are Kc, or the proportional gain, equal to 10, reset time tau I equal to 1, and derivative time equal to 0.5. Determine the equation and plot of the response. So with these given parameters Kc, tau I, and tau d, we are asked to find the response and the plot. Given by the transfer function for PID controller, we have P of S over epsilon of S equals to Kc, quantity 1, plus 1 over tau is plus tau ds. Substituting with the given parameters, we have P of S over epsilon of S equal to 10 quantity 1 plus 1 over S plus 0.5s. Since it's a unit step change in error introduced, so that's an epsilon of S equal to 1 over S. Substituting epsilon of S to the equation, we get P of S equal to 10 over S plus 10 over s squared plus 5. By taking the inverse Laplace transform of this equation, we get P of t equal to 10 plus 10t plus 5 theta t. So, plotting this response, we have this simplified equation here. And with the definition of impulse function, delta quantity t minus a is equal to 1 if t is equal to a, and 0 if t is not equal to a. So, if we let t equals 0, substituting it in this equation, we have P of 0 equal to 15. That's why we have 0 to 15 straight line here. However, with the definition of impulse function here, if t is not equal to a, we can get delta equals 0, which is this portion will be 0, and left with this equation 10 quantity 1 plus t, which is the slope. That is why we have this function here, p of t equal to 15 if t equals 0, and 10 quantity 1 plus t if t is equal or greater than 0.
For problem number 3, determine the transfer function C of S over R of S for the block diagram shown below. We are given the block diagram and we are asked to find the transfer function C of S over R of S. For the solution, analyzing this block, we have R times GC. In this junction, we have the negative C, so it will be RGC minus C. Following the path, we have G1. And in this second junction, we have positive R. Times all of that to G2, and it will be equal to C. So we have RGC minus C times G1 plus R times G2 is equal to C. Distributing, we have RGC G1 G2 minus C G1 G2 plus RG2 is equal to C. Combining like terms, we have RGC G1 G2 plus RG2 is equal to C plus C G1 G2. Extracting the R in the C, we have R times the quantity of GC G1 G2 plus G2 is equal to C times the quantity of 1 plus G1 G2. Transposing the terms, so we have C of S over R of S is equal to GC G1 G2 plus G2 over 1 plus G1 G2.
Problem number 4 states that for the block diagram below, determine the overall transfer function C of S over R of S and determine the response for a unit step function. Here is the given block diagram. For this problem, we are asked to find the overall transfer function C of S over R of S and also to determine the response for a unit step function C of t. Interpreting the diagram itself is a bit hard, so we must first simplify the diagram. First is to have a common comparator. As you have noticed, the comparator here still have the same operation as before, like the operation from R to the comparator, which is addition, and the operation from the above block, these two here, which is addition, and lastly, this below block here, this 25, which is subtraction. Next is to shift the takeoff point of this block after this block. Since we shift this, 2 will be divided by 1 over S. The above block will then be equal to 2S. Since this 2 block here is connected in series, we can combine these 2 blocks by multiplying both, which will then be equal to 1 over S squared. We can solve for this block diagram now, or we can still further simplify it. Now, interpreting the block diagram, so quantity R plus this above block here, which will be 2SC minus this below block here, which will be 25C, multiplied by this block here, which is 1 over S squared, which is equal to our controlled variable C. Distributing 1 over S squared, so R over S squared plus 2C over S minus 25C over S squared is equal to C. Combining all the expression that has the same variable into one place, so C minus 2C over S plus 25C over S squared is equal to R over S squared. Now, isolating the C and R, we get C quantity 1 minus 2 over S plus 25 over S squared is equal to R quantity 1 over S squared. Finally, we can now get the overall transfer function C of S over R of S, which is equal to 1 divided by S squared, quantity 1 minus 2 over S plus 25 over s squared. Simplifying this term, so our overall transfer function C of s over R of s is equal to 1 divided by s squared minus 2s plus 25.
To calculate the unit step response function for number 4, we will be utilizing the transfer function which was derived earlier, which is C of s over R of s equals 1 over s squared minus 2s plus 25. Since it is an input of a unit step function with R of s equals to 1 over s, substituting it to the transfer function give us this equation: C of s equals 1 over s times s squared minus 2s plus 25. Now, through partial fraction decomposition, when s is equals to 0, a is equals to 1 over 25. At s to the power of 1, the c value is equals to 2 over 25, and at s to the power of 2, the b is equals to negative 1 over 25. Hence, c of s is equals to 1 over 25s plus 1 over 25 times negative s plus 2 all over s squared minus 2s plus 25. With further simplification, we got this equation. And then, taking the Laplace inverse, we come up with the solution or the answer. C of t is equals to 1 over 25 quantity 1 minus e to the power of t cos 2 square root of 6t plus 1 over 2 square root of 6 e to the power of t sine 2 square root of 6 times t. And that's the answer for the unit step response function for number 4. Thank you so much for listening, and if you have any questions, feel free to ask any questions. And before we end, our greatest hope is that the Christmas spirit of goodwill and love fill the world and shine as brightly as the star of peace. Merry Christmas to all.